And here we are, another exciting session of probability. Actually, it's about our last session, a few final example problems to help solidify what we've learned. So here we go. Our first example problem involves that ever exciting enterprise known as an automobile assembly plant. And this one receives tires from two different suppliers. Now the first supplier has a defective rate of 10%, while the second has a defective rate of 5%. So let's suppose that we had 40% of the current tire inventory that came from supplier number 1. If a tire is selected at random from the inventory, and it is indeed a busted tire, determine the probability that the tire came from supplier 1. So the first and probably the most difficult issue involved in this is figuring out what our events are. So I'm just going to lay out the events. We're going to say that event A is that it is a defective tire, and event B1 is that it is a tire from supplier 1. B2 is, you guessed it, it's a tire from supplier 2. So these are our events, and being able to appropriately label events actually gets you halfway to where you want to get. Now what we're really looking for here is we want to know, given that the tire is defective, that it actually comes from supplier B1. Well, now we remember that we can write this in the following way. We can say it's put down in the denominator the world of probability of A, and then in the top we would say the probability of B1 times probability of A given B1. So we've already worked this whole thing out. Wow, well this seems pretty simple. We can solve for these kinds of things, can't we? Almost. We need the one last little trick, and that involves this idea that to solve for the probability of A, what we have to do is rewrite this expression as follows. I'm going to rewrite probability of A down below here. Remember, what we're doing is we're teasing out that information from the bits of A that lie within the different elements. So I'm going to write this out like this. B2 times probability of A, B2. So look at what we're doing. We're saying we're looking, this part right here is actually the probability of A intersecting B1, and this is probability of A intersecting B2. Between those two things, that is all of A. That actually is, so we can say this denominator can be, that is what that consists of, and that is all just the probability of A. So anyway, I'm going to circle this blue part right here because we actually know all of those factors within there, and I'll write those all out. But for now, let's continue on, and we'll write numerator probability of B1 times probability of A given that we're in B1. Okay, so that was the numerator, here was the denominator. Now we can write that whole thing, so we will do so. Probability of B1, well, that was just 0.4, right? It's given right here. And the probability of, given that we're in B1, what's the probability of A? Well, that's 0.1 from right here. Okay, so now we can take and divide by this, and we're going to write all this out. We already figured out this little part right here is actually the same as what's in the numerator, so we'll just rewrite it, 0.4 times 0.1. And then the last part is just, let's see, probability of B2. Well, it's actually 1 minus 0.4 is 0.6, right? That makes sense. And hopefully you caught that, because that's a little bit of a touchy point. So rewind it if you missed where I got that. And then lastly, given that we're in B2, what's the probability that the tire is defective? And that is 0.05, right? From right here. And when you work all this out, it turns out to be 0.57. And so in other words, the probability that given we have a defective tire, it comes from B1 or for supplier 1 is 0.57. Voila! Pretty nifty, I think. Okay, so we'll go on now to the next problem. And in this problem, we have that in the 2004 presidential election, exit polls from the critical state of Ohio provided these results. Oops, I hope you can read that. That's Bush and that's Kerry. And here's no college degree was 62%, college degree was 38%, and then we had various percentages that supported one candidate or another. So if a randomly selected candidate for Bush voted for Bush, what's the probability that the person has a college degree? And we can actually figure that out using some of the ideas that we've followed on before. Now, what I think is most important to do in these kinds of problems is simply to write down what we're really looking for. We're saying, given that a candidate voted for Bush, right, we'll call that B, what's the probability that they have a college degree? Well, let's call that A, right? So we'll say probability of given B that A occurs. So let me write that down here, that A is the event that somebody's got a college degree, and B is they voted for Bush. Okay, so we got that here. We've defined our events. We know what we're looking for. And so we'll say, well, in a nutshell, we always know the probability, not even thinking about what these actually imply. We can just say that's the probability of A intersecting with B over the probability of B. Now, how can we write those? We can say that just using conditional probability theorem, we know we can rewrite this numerator right here as probability of A, probability of B given A, right? And then the numerator here, probability of B, we don't really quite know what that is, but we can break it up again, just as we did for the previous problem. We'll rewrite that as, well, this can be seen as, overall, we know that there's the people who voted for Bush are going to be people who weren't college graduates and people who were college graduates. So in other words, we're going to say it must be the probability of A intersecting B plus the probability of A intersecting, of not A intersecting B. Right? That just puts into into the words what I just said before. So this is the same as this, but we can rewrite this a little bit more broken down in such that we can apply the numbers to it. And so we can rewrite this A intersects B as probability of A times the probability of B given A plus probability of A naught times the probability of B given A naught. And now we'll go back and we're going to rewrite all of this so you can clearly see the answer. So we've got probability of A given B, and that's probability of A, that's probability of B given A, over probability of A, probability of B given A, plus probability of A naught, and probability of B given A naught. Okay, so now let's put in actual numbers. Oops, let's get a little naught in there. Okay, and the actual numbers are probability of A is 0.38. That's from right here. And probability of them voting for Bush, given that they're a college graduate, is 0.53. That's from here. And then these numbers, probability of A, again, this is just what we did before. So it's 0.38 times 0.53. And then last but not least, we've got plus 0.62, which you can see is the complement here of 0.38. In other words, it's 1 minus 0.38 times 0.5, right? So it's given that they don't have a college degree, that they voted for Bush, and that's right here. So there we go. When we figure all of that out, we end up with 39.3821%, and that is the probability that, given that they voted for Bush, that they have a college degree. Voila. Okay, now we're on to a circuit problem. I love circuits. I'm always partial to them. So anyway, if we have a circuit operating from left to right, the probability that each device functions is shown on the graph. So we've got 0.8 or and 0.9. So each one can fail independently. That means that if this one gets hot, it's not going to actually fry this one. They don't affect one another is the premise of this. And what is the probability that the circuit operates? Well, we know that both this device and this device must function in order for the circuit to work. So we're really looking for the probability that left and right are going to function. Well, that is actually the intersection, probability of the left one intersecting with the right one. In other words, they both got to work or your circuit's cooked. So, intersecting, and we're told that they fail independently. Oh, it's independent. That means it's really simple. We can just multiply the two probabilities together. And this results in 0.8 times 0.9, which is 0.72, and that's the probability that the circuit will operate. So these series circuits are just as easy as, well, 2 pi, and so you would like to see those on the tests. So let's go on to one that's a little bit tougher, and that is a parallel circuit. So for parallel circuits, now you can have this device functioning or this device functioning, and the circuit will still work. So actually, the probability that the circuit as a whole will operate is larger than the probability of each individual circuit. In other words, this one's 0.95, this one's 0.95, but it's actually going to be, I don't know, higher than 0.95 that this circuit will actually operate. The plus, of course, is it's more dependable. The minus is you got to have two devices, so it's more expensive. So we've got what we're looking for is the probability that either T or B is going to be functional. T or B. Well, remember our little or. All right, there's our union with a little or coming out of it. Oh, okay. Well, I'm trying to draw an or there. Okay. So anyway, so that is going to be the probability of T union with B is going to be the probability that this device works. Because either one works, you're good. Well, let's see. That's a little bit tougher to calculate, but we can back into it using some information we had learned about earlier. We know that, and you may want to stop and pause this to think about this and make sure that you agree with it. Probability of T union with B is the same as 1 minus the probability of T union with B naught. I suppose the best way, maybe I can show you a little bit, is here's T, here's B, and we can say T union B naught is actually all this yellow space outside here, right? And so then if we take the whole sample space, that's like 1, minus this yellow stuff, what do we get back? This same thing. So we can rewrite it this way, and I know you're thinking, well, why? It sure seems a lot more complicated, but you'll see why. So the next step is we can use one of those earlier identities to rewrite this as 1 minus P times, or P, the probability of T prime intersecting B prime. This identity here, the prime was outside both, but I moved it inside so it affects each one, and now it intersects, and we can do that because there's an identity that says that that is true. Now you may start seeing why we're doing this. I'm going to take this part right here, and I'm going to rewrite it down here, and I'll say probability T prime intersect B prime is just P times T prime, or a probability of T naught times the probability of B naught, and in this case that is going to be T naught is 1 minus 0.95, right? So this value is this, and this one is actually the same thing, 1 minus 0.95. So it's actually equal to 1 minus 0.95 squared, 1 minus 0.95 squared, which is equal to 0.05 squared. And then that is this portion right here, 0.05 squared. So ultimately then we can say the probability T union B is equal to 1 minus 0.5 squared, and that is 0.9975. And see, I told you so. It's even more reliable than any individual circuit by itself. Let's see here. Here's your comic relief. We have well, I don't know if it's that funny, but I think it's just adorable. So these are the cutest little puppies. So there's your smile for the evening, daytime, morning, whenever you're looking at this. Okay, on we go. Now our next problem is, and it is the last problem. So it's an inspector working for a manufacturing company, and they've got a 99% chance of correctly identifying the defective items and so forth. And you can pause it now if you'd like, and you can read this through. Okay, so first thing we want to do is figure out this probability that an item selected for inspection is classified as defective. Well, we've already worked through this kind of thing quite a bit, so we'll just write it right out. Probability that it's defective has got to be the probability that it's, given that it's good, that it's classified as defective, times the probability that it's good, plus the probability that given that it's not good, that it's classified as defective, times the probability that it is not good. And so we can write all those out. This probability that it is classified as good is going to be, well, if we look at this, we've got 0.09% of non-conforming. So that must mean that we've got 0.991 of conforming. In other words, they're good. So we'll say that that is 0.991. And then the probability that given that it's actually good, that it's classified as defective, is going to be 0.005. See, that's from right up here. That's 0.005. So, and then we can say plus the probability that it ain't not no good, and that here is 0.009. That's from right up here, 0.009. And then lastly, we're going to have the probability that it is not good and it is classified as defective, and that is 0.99, which is from right up here. And when you work that all out, it turns out to be 0.13, well, 9. That's close enough to us, or to what we want, and that is the probability that it is classified as defective. Now, for part B, we want if an item selected at random is classified as non-defective, what's the probability that it is indeed good? So we can say probability, let's draw a little line here, probability that given that it is not defective, that it is classified as good. Well, okay, once we've written that down, we know what to look for. We're just going to say that's probability of good intersecting with not defective over probability that it is not defective, and that is just going to be probability that it is, well, we can rewrite this intersection as probability of D that it's not defective, or classified as not defective, given that it's good, times the probability that it's good, all over probability that it is not defective, classified as non-defective. And so that will be, let's see, this one right here is Well, if you look at this is saying, okay, item's good, and we've actually classified it as non-defective, which is a good thing. We already know that, let's see, chance of correctly identifying 5% chance of incorrectly classifying a good item as defective. So that must mean that there's a 0.995 chance of classifying, given that the item is good, we actually classify it as non-defective. That's, hopefully you can read. So what I'm trying to say is this number right here is 0.995. And the probability that it is good, we've already looked at that, and that should be 0.991. And now we divide it by the probability that it has been classified as non-defective. And that should be just 1 minus 0.0139 from what we got right up here, right? And so when we do all of this and we calculate it out, we should have that the probability that it is, given that as it has been classified as non-defective, what is the chance that it's actually good? Well, that's pretty darn good at 0.9999. So check, here we go, and that's all for today's wonderful session of a few final problems with probability.